Okay, well, welcome to Physics 1417, and we're going to start with Chapter 15, talking about the atom. This one's kind of pretty basic stuff, but we want to talk a little bit about the atom and what we know about the atom. First of all, the first thing we'll talk about the atom is that they're moving, okay? And for a long time, there was a guy named Brown. Don't remember his first name at the moment, but his name was Brown, and he was studying pollen grains, which are constantly, they put them under a microscope, and he noticed that they were constantly being jostled around in the liquid that he had to put water with them, and was looking at it under a microscope, and they were constantly moving around and vibrating. And even though there was nothing jostling it or anything like that, he said they're still moving around, and this was called Brownian motion. It was just small objects under a microscope that you'd see constantly jiggling around. Well, basically, it was explained by Einstein in the 1900s. Brown was like in 1827, and it was named after him, called Brownian motion, but he couldn't really explain why it was happening the way it was happening. And Einstein said basically the atoms were moving around and they were jostling the pollen grains. And so that's what was actually causing this. Now, atoms are basically invisible because when you look at them from a microscope, they are so small compared to the wavelength of light, they basically are missed, and therefore they're not big enough to make light bounce off of them and come back towards the light microscope. And so we don't see we can't see atoms in that sense. Certainly not with light. Light can't get anywhere close enough to it. Now, we can use scanning probe or electron microscopes, and basically it's somewhat even though they're about 100,000 times smaller wavelengths and have smaller they can see things up to 100,000 times smaller than a light microscope. Even so, it's how these electrons interact with the surface atoms, and they're detected and then kind of translated by the computer into a 3D image. But we still can't see them directly. And when we start showing the protons and electrons circling around, we call it a model because we haven't actually seen, it can't be viewed the way we can see like larger objects. And so we really don't know exactly. We got a model. And as long as the model explains how things work, and as long as we find things that work the same way, then we assume that we have a good model. If they don't work, or they don't work according to what the model says they would, then we throw it out, and we try to change the model and make it better. And the model has been changed many times over time. As we've gotten better and better idea, we've done more and more experiments to test it, and now we have a pretty good model of that. When we draw the atom, it's still not going to be exactly the way we think it is. I'm simplifying the model a little bit for what our purposes are. But for now, we'll go with that. But anyhow, one of the first things I found out is that one guy way back long ago, his name was Democritus. And this was back in the time when people were running around in togas and so forth. And he said that the theory is that things are made of atoms. And atomos was the word he used. And the word atomos means indivisible. All right, that's in our Pledge of Allegiance, one nation, indivisible, which unfortunately is not true. It can be divided and has been at various times in the past. But at any rate, the idea is it can't be divided. And what Democritus said, if I get a piece of gold, I can cut it into two pieces. And then I can cut those into pieces. And eventually, though, I'm going to get to a piece that is so small, I cannot divide it into anything smaller. Okay? And he said that is an atomos. Okay? So if you take a substance and get to the point where you can't divide it into anything smaller, that smallest piece of something, that is an atomos. All right, and we use that as the word atom that we came from. And we kind of basically agree with that. There is a small thing. Now, we have split atoms, divided atoms, very large, unstable atoms like uranium. Okay, and we have caused them to release enormous amounts of energy when that happens. Very difficult to do. The only ones we can do are the very largest, most unstable atoms. But he was still right in the fact that once you divide things, they are still an atom is the smallest particle that it would still be. If I took a gold atom and I have one atom of gold, now I couldn't see it because it would be so small, but if I could see it, it would still be gold colored. It would still melt at the same temperature. It would still be able to hammer it and flatten it out. Okay, it would still have all the characteristics of gold. If we split an atom, then like uranium, we do the big atoms for uranium, it's no longer uranium. It will split into smaller elements, lead and radium and some other byproducts as it comes down and breaks down and decomposes. But basically, an atom is the smallest piece of a substance that still has the characteristics of that particular element that it is. Okay? And elements, though, we have learned are made of smaller parts. Okay? And we call those smaller parts subatomic particles. Sub means below, just like submarines go below the ocean. Subatomic, smaller than the atom, below the atom. Particles, just parts, basically. Parts is parts. In this case, they're atomic parts, so they're subatomic particles. All right, and of those three, we have protons, neutrons, and electrons. So we have protons, neutrons, electrons. Now, some of the characteristics we need to know about these mostly have to do with their mass. How much is there? How much stuff makes them up? How big are they? And their charge. Do they have a charge, positive and negative? Remember, electrical charges are what hold the world together, basically. And so we need to know what the charge or electrical charge of these atoms would be, or parts of the atom, particles, would be. Okay, so let's look at, first of all, the charge. Protons have a positive charge, so we put a P positive. They have a +1 charge, so a lot of times that's the symbol for protons, is P with a positive sign. Neutrons, on the other hand, are neutral, so we put plus minus up there just to show that they are neither positive nor negative, so they don't have a positive or a negative. They cancel each other out. They have no charge. Okay, they do have mass, so we'll talk about that in a minute, but they do have charge. Okay, now the final thing is the electrons, and the electrons have a -1 charge. Electrons are very small compared to protons, but their charge is equal to it, but opposite. So we would say that they have a -1 charge. All right. Now the mass of those, when they first started looking at these, they said, okay, well, let's figure out what the mass of a proton, neutron, electrons would be. And they said, well, we're going to do it in the same units that we do mass in for other things, and that is grams. And so it's 1.673 times 10 to the -27th. This would be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 1673 grams. Now, that is a very, very small number. And they said that's just kind of unwieldy to work with. It's just too big and things. So let's make up a whole new unit. And they made one called AMUs, which stands for Atomic Mass Unit, which makes sense. Because basically, sorry, didn't do that U there, I guess. But atomic, it has to do with the atom. It's a unit used to measure the mass of an atom, and that's basically all AMU means, atomic mass unit. And since we can make it up, they said, let's make it something nice and even. Let's just say 1 proton is equal to 1 AMU. All right, and that will make it very easy. So if we just count the number of protons, then we know how many AMUs the protons weigh, and that makes it fairly simple. Now, neutrons are 1.675 times 10 to the -27, okay, and that's also a very small number, but it's basically the same as the neutron. So for practical purposes, we say that they measure 1 AMU also. However, they are slightly heavier. Okay, so if we said they're exactly the same, that would be incorrect, but for practical purposes, it's close enough that we say that they are the same of 1 AMU, but technically it weighs a little bit more. Okay? Now, an electron is equal to 0.0000239 times 11 times 10 to the negative 27. Okay, so to put it in scale with the other ones, compared to them, it's still itty bitty. Okay, so we basically say that it has a mass of 0 AMUs. Is that technically true? No. Okay, it has to have mass. There is a mass there, but it is so small, okay, that we basically can say that it has no AMUs. It's kind of like if you have an elephant. If a fly lands on an elephant, does the elephant, if it's sitting on scales, would it weigh more now? Yes, technically. But the weight of that one little fly, the mass of that fly compared to the mass of the whole elephant, is so small that it's really not significant. And so basically we can say, for practical purposes, the electrons have a mass of 0. Okay? Now if you think about it, if you add an electron to a neutron, sorry, if you add an electron to a proton, which is negative and positive, the charge would be neutral and it would weigh a little bit more. Okay, and so it's not quite that simple, but a neutron is almost like a proton plus an electron because it's neutral, has no charge, and it has a little bit more mass than the proton does. We'll talk more about that later in the next chapter, but that's almost kind of like what they're like. Okay, now, of these, where are they found? Well, first of all, you have protons and neutrons, and they are found in the center of the atom, which we call the nucleus. Okay, not to be confused with the cell nucleus, but on the other hand, kind of the same general idea. Okay, and a nucleus is in the center. Now, sometimes we draw a circle around that. Really what you're saying is you have all these little particles in the center of the nucleus, and that would be the nucleus. There's no border around it or anything like there would be in a cell. It's just those particles are there, okay? And they're all held together. Now, why do you need to have neutrons? Well, think about it. If you have protons, protons have positive charges. Let's just say there's a positive, there's a positive. If you have all these positives together, like charges do what to each other? They repel. Okay, and so they repel each other. Well, all these protons would repel each other. So instead, they have neutrons that are in between them. Sorry, you can't really see that, but let's just say it's a neutron. And so the neutrons help kind of space out. I'm just going to color them in here. And they help space out the protons so that they hold them together. There's what's called the strong nuclear force that holds them all together. And this is what we release when we split an atom. We're actually splitting the nucleus of the atom. We're breaking that nuclear force, and that's what releases the energy behind an atomic bomb or something. So this is a very, very strong force, and it helps hold those neutrons and protons together in the center. Because of this, you almost always have at least as many neutrons as protons, and usually more. The only exception for that is element number 1, which is hydrogen. It has 1 proton and 1 electron. And so there's really no need for a neutron because neutrons help hold the protons together and keep them from repelling each other. But if you only have 1 proton, you don't really need that. All right. So we talked a little bit about the protons and neutrons. That's the nucleus. All right. Now let's talk a little bit about the electrons. So say we have, let's just say we're going to make an atom here, and let's just make it oxygen, which has 8 protons and 8 neutrons. Now I could draw all the little circles for those, but I'm not going to. I'm just going to leave that to represent that. Now the electrons circle around that, kind of like the moon circling around the sun, but instead of gravity, we were talking about electrical charges that are attracted. All right, and so they are attracted by electrical charges. I put 2 electrons in this outside layer, and so it has 2 negative electrons, and they're attracted to the positive here, and that keeps them from leaving it. But the energy of the electron, this has its own speed, it keeps it from being sucked in. It's going so fast this way that the pull of the electron still keeps it on its level. Now, the next thing it will do is, if it's full, once it has to be, and there's not enough room for any more electrons, so it goes to the next energy level. And we call these energy levels because the more energy they have, the farther away from the nucleus they can move. All right? And so we have different layers of orbitals or energy levels that electrons stay on. And we will finish that thought when we come back on part 2.